why I talk about discriminative models, it's to kind of get at the idea that we're going from, when we go from discriminative models to regressive models, is the idea that we're going from generating a small dimensional output conditioned on some input, high dimensional or low dimensional, to going to the limit where we are generating high dimensional outputs. We then talked about variational autoencoders, and exactly as you say, variational autoencoders are models that both compress and then try to expand data to regenerate, just exactly as you said. And the idea there is that what you hope is that in the compressive step, you learn some variables, you learn some representation that is somehow useful for understanding what the underlying governing characteristics of the data you're learning on has. And the hope is that if you train on that set of data, or you train on that set of data, you can now pick things in that very low dimensional compressed space to generate back high dimensional examples that are novel and exciting and different.
So we'll get started. This is ideally, I think this will be our 20th episode. I have not checked the numbers anymore, but 20th episode of our Generative AI in Enterprise series. And Vedant, thank you for coming in. This is our third time that we are meeting, and we have one more to go. In the last one, we want to do a more casual conversation. Today's topic will be, I think, more intense and deep dive into technology and trying to create some codes. But before that, I want to go through my understanding of what we have discussed till now. And you can correct me if I go wrong at some point of time. So basically, the way our discussion started is like, we are all like excited about generative AI and ChatGPT and all those things, but you gave us a different point of view altogether, right? So it's like understanding discriminative models. So based on my understanding, discriminative model is a type of model which is used in machine learning and statistics that focuses on distinguishing between different classes or categories of data. It learns the decision boundary by that separates different classes by modeling conditional probability. Now, what does that mean? So that means an example of that is linear regression, and linear regression is typically considered a regression model, basically predicting continuous values rather than classes. But it also can be adapted as a discriminative model with several techniques. But then your point was, can this discriminative model generate data? Right? I think that was the point, right? Can this discriminative model generate? And what do I mean by that? That discriminative models are not designed to generate new data. It can classify or predict based on existing data. So I want to understand that portion a little bit more, but I'll complete my thought. But I still have a little question over there. So it can classify. Basically, you were talking about grouping and latent spaces. Most likely, that's where we are going to connect. But it can classify based on existing data, but it cannot generate data. But then, for example, like linear regression, continuous value given input features, but not inherently generate new samples from the input distribution. So that's what my note says over here. I want to kind of like touch base on that part a little bit more. So then we talked about like how an argument can be put together that for a discriminative model as a form of generative model, right? So you're saying, okay, how can we make a discriminative model generate new data sets? And then we kind of like explode into generative models altogether. And then the whole concept of exploding new dimensional data came into picture. And then you introduce us to variational autoencoders. Now, typically autoencoders, based on my understanding, is it tries to compress data, and then I should have the ability to regenerate from the compressed data, right? So now you introduced us to one of the, out of like several neural networks that are available. VA is one of them. And then you introduced us to VA. And then you said, okay, if I'm giving more dimensions to the data, maybe we should be able to extract or generate data out of those VA models. I think I'm getting lost a little bit over here. So I'll need your help to connect the dots. But I tried to summarize my best.
Yeah. No. So maybe I can help out here.
Yeah. Okay.
So good. Where we started was like I think what you said was exactly correct, which was we were looking at what's really changed, what's been the paradigm shift in the past couple of years, and for a long time people thought about machine learning in the context of these kinds of discriminative models, and as you say, discriminative models are models that are useful for classifying and things like that. And in some flavor, I often think of linear regression as the discriminative model because you can think of linear regression as sort of like, okay, let's classify which quantile this data point fits into or something like this, right? I think there's maybe it's actually somewhat imprecise to call linear regression a discriminative model. That's my bad, but I would at least kind of rely on this formalism to think about things. Now, why talk about linear regression? Why talk about discriminative models? It's to kind of get at the idea that we're going from, when we go from discriminative models to regressive models, is the idea that we're going from generating a small dimensional output conditioned on some input, high dimensional or low dimensional, to going to the limit where we're generating high dimensional outputs, right? So going from generating the label of a picture or the home price, given a bunch of statistics about what things to govern home price, to generating an image given another image or something like this, or generating a sentence given another sentence, right? That's the idea of going from high dimensional input to high dimensional output, or whereas the earlier case was about that high dimensional input or low dimensional input into a low dimensional output. So I would say that was kind of the core distinction there. We then talked about variational autoencoders, and exactly as you say, variational autoencoders are models that both compress and then try to expand data to regenerate, just exactly as you said. And the idea there is that what you hope is that in the compressive step, you learn some variables, you learn some representation that is somehow useful for understanding what the underlying governing characteristics of the data you're learning on has. And the hope is that if you train on that set of data, or you train on that set of data, you can now pick things in that very low dimensional compressed space to generate back high dimensional examples that are novel and exciting and different. And so this is sort of, I think, the...
Good. So, I mean, in the next meeting, like 2 weeks from now when we meet, I'm going to dive deep into transformer architecture and why we need, like, why do I even need VAs and why not transformer architecture? So that kind of a discussion, but I'll leave it for now. Yeah. But I'll just quickly run through the other pieces of topic. Like while we kind of like went through that whole flow of thoughts, these are some of the pieces of topic that kind of like came up. So yeah, 1 second, sorry.
Yeah, so there's a lot of like little concepts here and there that got introduced as a part of this process. So a lot of the was different statistical tools or different probabilistic methods that are useful for understanding how these models learn and how they are trained. So Bayes' theorem and Bayesian methods is exactly one example.
So I'll give you a little bit of my understanding from my notes over here. So we talked about Bayesian methods, and where it says that we can estimate model parameters by maximizing the likelihood of data. This approach helps us understand the underlying distributions and improve our models. So that was a methodology or a technique that was improved to help us understand the underlying distributions and improve our models. And from there, we went on to like regression to generative models, like moving beyond simple regressions and generative models, focus on probability distributions, etc., etc. Then we introduced into VAEs, and where we are generating new data points. They use latent space representation to cluster similar data points, make it easier to generate novel examples, right? So we kind of like touched upon that. We during our discussion, we also touched upon like auto-regressive models. And I had a question like, what is auto-regressive models and all? So at that point of time, we discussed that, okay, these models predict sequences by relying on previous data points. So that's where it becomes a little gray from our layman's terms of view. Like, oh,
Sure.
what are the difference? I mean, both of them seems to be like generating stuff, right? So how is this auto-regressive different from VAs? But I'll hold you off over there because I know like you have a lot of things to say. But I'll just quickly summarize our understanding over here, right? And then we kind of like talked about challenges in generative. Oh, so part two, which is last week, we went into generative models, create new data by modeling distributions. VAs, for example, are used to generate biological sequences by clustering data in latent space. So you were giving all these examples about like how you can create new protein sequences by giving a sample, right? And creating that latent space. You also talked about principal component analysis, which is PCA, that helps us understand the structure of the data by reducing the dimensionality. Very, very interesting concept. I think that's where um, it is often compared to VAs because in VAs you were talking about the same thing, similar, right? I mean,
Yeah.
you were reducing the dimensionality and again expanding it. We often compared to VAs in terms of understanding data patterns.
Hmm.
You also talked about covariances, second order statistics. And so basically these concepts revolve around like how small changes in data, how small changes affect the whole data structure.
Yeah, you might say it is like how a change in one variable or one feature of a
Gotcha, one
vector,
feature. Okay.
yeah, impacts the other features.
Right. And then
Yes.
which is like allows us to cluster similar sequences and generate a new one. For example, this representation is vital in for tasks in creating protein sequences.
Yeah,
Dimension.
I think the thing to take away there is that when we talk about sort of latent space representations and things like this, like we have these very complex models, right? These complex models that project that serve as basically functions, and they map from the input space, right, the feature space, to some dimension, some space inside before mapping back to a space that we can interpret. That's that intermediate layer that we call that is like a latent representation or a latent space, right? And
So
so that's high dimensional, low dimensional, whatever. Like that can depend. For variational autoencoders, very particularly, it is chosen to often be low dimensional.
is variational autoencoders only used in biology and protein sequences? No, right? I mean,
Oh, it's
it's
fairly broad. It's
broad.
fairly broad.
Definitely.
I think yeah. I mean, it's a fairly broad tool. It's used
Yeah,
in a
of
couple.
course.
It's used in
Yeah.
many contexts. Yeah.
But you just used it as an example, right? As a
Yeah.
reference. Yeah.
Yeah. I mean, I think I used it because it's like sort of a interesting and simple enough to understand example of generative machine learning.
It's an architecture. It can be used in any place. Why would I use VAs and not transformer
I
in your
think
protein sequences and all?
well, I mean, I think that like these days I think everyone wants to use transformers and will like it's just a matter of like how expressive you need your model to be.
Oh.
One sort of maybe nice thing about variational autoencoders is that projection to that low dimensional space
Hmm.
can offer you some level of interpretability that you might not be able to get from transformers. Although like I think there's enough effort now going into like actually building approaches to interpreting transformers that maybe variational autoencoders will just be obsolete in a couple of years time.
Okay, so things keeps on changing. So new architectures come up. I think VAs were, if I look at the timelines and all VAs, when did VAs come out?
2016, I want to say.
Okay,
Not terribly old.
no, 2013. I have
2013, yeah. It's like 10 years
2013.
old, not that old.
Yeah. So and then Transformers came around like 17,
Yeah, I think 16, 17, something like
16,
that.
17. Okay, and then interesting another concept. I'll let you drive our next part of the discussion. But another concept is this compression, compressing the data as well as like expanding it, right? So it's the way both of them, whether the transformer as well as VAs, both of them has the same similarity, right? Where I kind of like create a high dimensional or compress the data through the encoders, and then when I decode it, it kind of like recreates that same structure.
Yeah, so actually, I guess it's not guaranteed that transformers are compressing. I think sometimes they project to higher dimensional spaces than the input spaces. This, I think, depends upon exactly the transformer that we're talking about. Like, I don't know the exact layer sizes of of BERT or something like this. I don't know off the top of my
Okay.
head, but it's out there, and I'm sure like it's not obvious to me that it's necessarily going smaller or larger than the input dimension.
Okay. Sounds
Yeah.
good. So I'll stop over here. I think I did not do the disclaimer part, so I'll just quickly touch upon that for new people who have joined. So this session is being recorded, and I'll share this session. Typically, I share this session in YouTube and other social media. So if you are not comfortable with your camera or your phone, if not comfortable talking, please keep that in mind. But we still want you to participate, get into the discussion, so that way we can have a nice conversation. Also, this whole meetup group is my own personal initiative, nothing to do with my employers' strategies or positions or nothing like that. So that's pretty much done with my disclaimer. Little one-liner. So go ahead, Vedant.
Okay. Awesome. So yeah, I figured today we'd take the opportunity to explore how we might build a variational autoencoder from scratch. And I mean truly from scratch today. And I haven't rehearsed this or anything like this. I'm relying purely on uh, a mixture of memory and Google to solve through this, but I think that's not terribly dissimilar to the way I approach doing my job on a day-to-day basis. So it'll be a live demo to show you how I solve some of the problems that I might see as I'm working through building up the architectures for one of these models. So I'm going to share my screen,
That's beautiful. Yeah.
and I'm going to
Good to
start
see
straight up from a
something.
terminal window. This is my terminal window right here. Y'all are seeing exactly the way my PC is organized in all my files. And what we're in is right now just a directory that I've created for this particular conversation called Scratchwork, and all it has in it is one CSV file that has the data that we're interested in. This step at the very least of creating an environment, a Python environment to work in and do your work, is fairly universal. I think everyone kind of does it. The actual sort of environment and package manager you might use might vary. I tend to use Anaconda pretty heavily. So for the purposes of this conversation, we'll create a Conda environment. Um, and we'll call this CC demo. I'm gonna put in Python.3 into this environment. I'll put torch, pandas, matplotlib for so torch for obviously your machine learning slash autograd framework, pandas for reading through your CSV files, matplotlib for reading your making plots and things like this. Num or I guess NumPy. I like to call it NumPy for some strange reason. But just for doing a little bit of numerical computing and things like that. And maybe TQDM just give us a progress bar. Oh, and Jupyter Lab so that we can make a Jupyter notebook to work in. This might be enough. It might not. I don't know. We'll as I often do, I realize I need a package later, and we'll just install it when we need it. So we're going to give this a few seconds to kind of construct the environment. And in the meantime, while we're doing that, we can take a quick peek. Oop. Oh, I guess Conda Forge doesn't have this. All right, my bad. We'll do this again. All right. While that's running, let's take a quick peek over at the file that I put in there. So if we look at this file, what you can see is it's effectively, so this is a file that I downloaded from online somewhere. What you can see is it's basically just a spreadsheet, a CSV file, which has a bunch of information about sequence data that we're working with. So there are sequences unaligned. This is truly like just the amino acid sequence that corresponds to a particular protein or something like this. And what we'd like to do in the course of this thing is build a machine learning model that can generate novel examples of a sequence. And doing that will be quite useful because if we wanted to generate novel examples of a picture, it's not terribly dissimilar or something like that. So we can see that our environment has now been created. I'm going to go ahead and activate it. And now we have to go through the process of just quickly pip installing all of our pip install torch, TQDM, Jupyter Lab, matplotlib. We'll take the time to quickly install all of our packages so that we have them all at our disposal, and then we'll get to it. I think I forgot to install pandas there, so we'll just do it. We'll take another step to install pandas.
That's okay. So in the meantime, can you also show us the CSV file that you're talking about?
Yeah. So back to the CSV file, you can see there are several columns.
Okay.
names of the different proteins and what they are, the sequences they correspond to. This particular data set in biological sequence data, you often refer to.
Are you sharing something? We are not able to see. We
Oh,
only
I'm
see the
sorry. I apologize. So, as you can see on the screen, we have a big table. The table has several columns: source, where is the sequence pulled from, accession number, which I forget exactly what this means, but it's not super important. Header, which kind of gives us a name for what the biological sequence we're looking at for is. The domain number, which is corresponds to, so phylogenetic classifications, domain is one of the classifications for biological organisms. This is a number that maps to that. You have the sequences themselves, so the amino acid sequences. Our objective is to generate new examples of these from a model that fit in some particular way. And uh, typically biological sequence data is either kind of fed through an alignment or something like this, just to make everything the same dimension. So the unaligned sequences are over here, the aligned sequences are over here. Alignment is its own like beast that we don't want to talk about in this conversation, but it's like just to think of it as a way of making data that is of different dimensions of the same size. And that's kind of useful because when you feed things into a neural net, like neural nets are kind of inflexible in that they always expect things to be the same size. Um, and then, the authors of this paper, the piece that I downloaded this from, they made their own generative model and put it into some space, and they've been nice enough to report the coordinates of their generative model. They've also given us the phyla for which these, like the phyla of from which these sequences are pulled. So another, like speciological, I don't know. Another sort of like species level type classification. It's kingdom, domain, or domain, kingdom, order, phylum, uh,
Okay.
whatever, family, genus, species. So this is phylum in that tree of classifications. And then normalized relative enrichment represents the relative activity of each of these sequences. Cool. So it looks like our thing finished installing. I will quickly check to make sure I have everything that I want. I'm pretty sure I forgot to install pandas. It's not in the list. Yeah. All right. There we go. And once we have that, we will hop over into a Jupyter notebook. So now I will show us the Jupyter notebook that I'm working with. So also, if you all are very, very familiar with this, I'm sorry if it's a little boring, but we're going to quickly import all of our relevant packages in the standard data science way, our standard like standard coding way.
Programming, yeah.
Yeah. So I'm going to go ahead and read in our. Oh, my computer is slowly importing all of our packages. So we're going to go ahead and quickly read in our CSV using pandas. Take a quick peek and see if I messed anything up or forgot to do anything. Nope, we're good. So we can see that we have our CSV kind of similar to the way we had shared it earlier. Same columns, everything kind of as a habit. Like pandas is really nice and pandas is really nice for small enough data sets that can fit onto your RAM or something like this. If you were using a much larger data set, you might use something like Spark, a Parquet file, an Arrow file, or something like this. But all of these kinds of things are based on like syntactically at the very least, and I think even programmatically very similar to SQL. And like you can use a lot of your custom SQL, your common SQL commands like join, merge, group by, et cetera, to do a lot of the data manipulation that you want to do. So for example, if I just wanted to read the sequences column from this data set, we can just quickly call that column. So one thing that's kind of worth noting right here is that a machine learning model is going to want everything in terms of numbers, right? It wants everything as matrices and numbers. It's not going to be able to just read in letters in this particular way. So the first thing we have to do is we actually need to build an object that's going to take in this sequence data and actually convert it to some numeric representation. So in order to do this, the very first object you might need is a dataset class. So we're going to go ahead and build a protein dataset class.
Is it
So
similar to embedding?
No, this is like much more this is much more naive than that even.
Okay.
This is like, so you have raw data, right? This is basically raw data. And what we're trying to do here at the very first step is convert that raw data into a matrix representation. And this is often like just using lookup tables or
Okay,
something like
okay, okay.
this.
Got it.
Like
Okay.
very straightforward, just try to convert everything from letters to zeros and
Yeah,
ones.
yeah, yeah.
If you were working with natural language, like words or something like this, you use something called a tokenizer to do this kind of thing.
Hmm.
Um, Cool. Let's see. So the object we're talking about is called a torch uh, data set object. So if you're not familiar with what torch data set objects look like, this is sort of the page that serves as a tutorial for this. And we're going to create a custom data set objects uh, that's going to be used for converting this sequence data into numbers. So a class to convert uh, sequence data into numbers. Uh, so for right now. We don't need from here. Good. And we'll initialize this class always with sequence with some object that sequences that is going to be like an NP array or a list of either a NumPy array or a list of lists that has all of the sequences. And maybe that's pretty much all we need, actually. I think
Hey,
that's pretty.
there is a question.
Hmm?
Can you repeat what's the goal of the system you're building?
The goal of the system is to build a variational autoencoder that's going to generate novel examples of the sequences from the sequences that we have in this training data set. That is the goal. Let's say self equals six. And I think that's pretty much all we need from this. So one of the very first things we'd like to do is we'd like to build a method that's going to convert all these characters into some matrix of some sort. And what we're going to do is something called one-hot encoding. If you're not familiar with what one-hot encoding is, there's plenty of text about it out there. But what it basically does is it says, okay, so if I had a sequence like let's say A, B, A, or something like this. Um, and I wanted to one hot encode this sequence in the character dimension. We see that there are only two possibilities at each position for a character, right? It's either A or B. And so for each position, we're going to create a feature variable. And so we'll make this a markdown now, right? For each position, what we'll do is we'll say, okay, there's going to be one feature, there's going to be two features for every position because you can either be an A or a B, right? Uh, who knows? I should have made it simpler on myself by not putting so many. Let's just do three. So you can see I've created six spaces there, six dashes there. And what we're going to say is the first, for each of these sets of two, the first one will be one if it's an A in the first position, and the second one will be one if it's a B in that position. So in the first position, this is a one, this will be a zero, right? Because it's an A. Now we need to figure out what to populate the next two with. 0, 1, right? Because it's a B. Then we need to populate what the next two was. Good. If this is like super familiar to everyone, please let me know. But this is sort of like a very standard trick to convert like sequence data like this into some useful numeric representation. And what we're gonna have to do in our data sets
If it's like A and B, you have 0 and 1. If it's ABC, what would be the
sure. So let's say it was A, B. So
Mhm.
now there's three possibilities at each position. So we're actually going to give each position,
Okay, I see.
yeah, possible features.
It's still the binary digits over there. 0.
Yeah, it'll still be the binary digits, right? So in this limit, like, good. So that was a zero, and then we have 0, 0, right? Like something like this, right? So these three correspond to the first character. These next three correspond to the second character. These next three correspond to the third character, and these next three correspond to the fourth character. Cool. So what we have to do is we have to find a programmatic way of building up this exact methodology, right? So what we're going to go ahead and do is we're going to go ahead and code that up. So this is like maybe the first kind of challenge that one faces when one builds a machine learning model is like how do I convert my raw data into something that can be processed by a deep learning model? And I've kind of like now described at this stage like what the actual approach I'm going to be taking is. So in order to make this work, what I'm going to first do is I'm going to say, okay, let me just make myself a mapping, like a dictionary mapping. that just says like, let me create a dictionary mapping that just it has like maps a character to an index value. So we know that for amino acids there are this many sequences. Sorry, there are this many characters. You can have 21 characters plus a 20 characters plus a dash. Oh wait, IDX to AA? Yeah, IDX to AA. That's just gonna be this thing as a list. So that you can see what happens when I run these commands. We can go ahead and take a peek. So amino acids, I've just named a variable IDX to AA. Good. Maps, turns everything to a list. Why is this useful? Because now when I specify an index, I get back a character. That's an amino acid. Specify another index, get back a character. That's another amino acid. We actually need to flip this. We want to get amino acids to indexes, right? Because what we'd like to do is we'd like to specify in our one hot encoding which one of these should be turned into a one, right? So we're going to create self.aa to IDX. That's going to be dictionary for ourselves. AA self. How do I want to do this? How do I want to do this? Right, there we go. Self.idx. So what's going to happen here when I run this particular line of code? Where it's going to create exactly the map we just discussed. I flipped it. Perfect. Right now we can feed in a character and we can get back an index value, and that's the index we're going to activate for every single one of our characters. Right. This is going to be massive in the end. Right. We're going to have 21 possible zeros at every single for the length of the sequences. Right. So I got to flip this back. Right.
Isn't there a function to do this? Like, I mean, just call that function, give the sequence, and it's done.
Yeah, so you can use the inbuilt sklearn ones.
Right.
You can use the inbuilt sklearn ones. I tend to, for whatever reason, I tend to prefer coding these things up by hand.
So that I understand like what's going on.
Yeah, precisely. So when you build a datasets object, you always need to define a method called len. This is sort of a requirement of the class. We need self as a parameter here. Of course, this is the length of your data set. When you call this is a number of data points in your data set. And in particular, our number of data points is going to be given by the number of sequences we have. So we're just going to return self.seeks. And we're going to say, okay, seeks is probably, seeks again is a numpy array or a list of some kind that has the sequences in it. The other sort of requirement that you are obligated to have when you're creating a datasets object is get item. So get item is basically a method that you can pass so that you can pass the class an index and it returns the XY pair associated with that index value. So for this particular thing, we're going to return an XY pair, and this XY pair will be a dictionary for us. And X needs to have a few it needs to have a few parameters, right? It needs to have the inputs to the model, and then Y needs to have the outputs to the model. In our variational autoencoder case, as we've discussed, that's a sequence to sequence model. You input a sequence and you get back out a sequence, right? So X, the only key in X is going to be the seek, and it's going to be the one hot encoded representation of the sequence. Similarly, Y will also be, Y, the output of this should also be the sequence, and it's going to be the one hot encoded representation of the sequence, right? So now we need to build a method that actually does the one hot encoding, right? Cool. One hot, cool. So we'll say this is going to run one hot, and it's going to give back the one hot encoding for the index sequence that we chose. Of course, this could just be copied over here, but whatever. We can just run the function again. This is not intended to be like crazy optimal or anything like this right now. It's just supposed to work.
So while you do that, I mean, so you took a sequence. Now you defined what is one hot encoding, like or the length of the sequence that you have to reach. You have to read each letter with the length of the with either 1 or 0.
Precisely. Yeah. So we right, like so.
Now you're trying to generate the one hot encoding for that particular sequence using the method that you're writing.
Yeah, correct. That's right.
Okay, sounds good. And the reason why we are generating this one is because we need a numerical representation of the protein sequence.
Right. Precisely. Good. So we're going to start off with a seq vector, and that's going to be a matrix of zeros that is going to be. So earlier we talked about this particular representation for one-hot encoding, but it can be more convenient to actually think of it as follows.
Hmm.
So basically we have a list of lists or an array. I think it's easier to think about it as a tensor, where each row corresponds to one of the characters,
One of the characters.
and the values in the row specify which one of the which letter is that character,
Correct. Yep.
right? So we're gonna do exactly that. We're gonna have len sequence. We're gonna have how many characters are in the sequence, number of rows. Len self dot idx to AA. Perfect. Okay. We're gonna have and then we're gonna have the length of the list, length of the number of amino acids as the number of possible values that could be in each row. Remember that most of the for every single row, every single one of these values is going to be zero except for one value per row, right? Because you can only have one letter at every position. Cool.
Okay.
So now we have the very simple task of just iterating over the characters
I
in
have
the
another
yeah,
question. Why one-hot encoding? Why not take the ASCII value of that particular letter and then convert it into binary?
Good. So the reason to do one-hot encoding, it tends to be a choice that one makes, but what you're describing, so okay, there's kind of like several flavors of numerical representation of data,
Yeah,
one of which is one-hot encoding, which has this particular structure. It's
Mhm.
not very space efficient, right? It's a lot of letters per, it's a
Exactly.
lot of numbers for every single character, right? You could do something like ordinal encoding, where you say, okay, look, the letters A through Z, we can number them 1 through 26,
Or maybe like
right?
ASCII, we already have the numbers defined 65A, right?
Sure. Same idea, right? You have a
Yeah,
you have a single number that represents these things, and these numbers are from like you can count them up. They can count up
correct.
to as high as you want.
Correct.
But the thing about that is that that imparts the idea, like it imparts a heuristic bias into your model that somehow Z is larger than A,
Oh, okay.
right? And Z is not explicitly larger than A in many meaningful contexts, right? Like, yes, there are some meaningful contexts in which you could say A is bigger than Z, and maybe that's because you're thinking about frequency tables or something like this.
Hmm. Okay.
Excuse me. But
Interesting.
but generically that's a bias that you don't want to necessarily give your model or have to worry about your model like having to like unlearn, right?
Hmm.
So
Okay.
this is why you might prefer this encoding style instead. There are many ways of encoding data for sure. Like this is just one of them, and ordinal encoding is another. But you kind of have to make this like you make that choice with like kind of a thought process. Like you want to make that choice with a thought process in mind, right? So now we're going to go ahead and iterate through our sequence. We're going to pull a character from. We're going to pull the index value of that character and then a sequence. And what we're going to do is say, okay, we have our seq vector. We're going to populate that row, the indexed row.
You have a typo in enumerate.
Ah, good catch. Thank you. I should see the text doesn't turn green. Self dot. And now we're going to use that handy little dictionary that we created earlier that brings us back to an index. That brings us back to the column value that we're populating. And we're going to turn that into a 1, right? And that's all we need. That's truly all we need for this task. And then we're going to go ahead and return seq vector. And I guess I should have specified the D type somewhere here. That's useful. And I think this should just work. So let's go ahead and give this a shot and see what happens. Okay, so let's just pick up a random sequence. We'll say seq equals, all right, what do we pick up here? We picked up one sequence. Let's define our method. Oh, I forgot to close it. Good catch. So, and now we put in one hot encode seq. Oh, I left that in. That was unnecessary. Perfect. Now I have some tensor that is this exact thing. So let's take a quick peek and see that it's right. So one hot encoded seq 0. So we're looking at the first character and it's saying, okay, the 20th It's the 20th index, which is or 19th rather, which has been activated. AI to IDX, what is 19? Oh, no, sorry. IDX to A, what is 19? It's a V. Seek 0. That's a V. Perfect, right? We found this was the 1 is positioned at the 19th index value, and then when our IDX to AA, that corresponds to a V. So now we can map from our sequences to our tensor object. So we have this nice little numeric representation that we can feed into our model, which sorry, I should bring this back up. Cool. So this is pretty much like the first step in any, I think, machine learning, data science, like, or not, maybe not the first step, but this is like when you actually decide, okay, I know exactly that I'm going to apply a machine learning or artificial or AI method to a data set or something like this, and I'm going to code it from scratch or something like this. This is kind of one of the first things that you need to do is you need to pre-process and massage your data into a structure that is amenable to a deep learning model. Awesome. So we have this method built up now. I had that typo that I needed to fix from earlier. I think everything else is pretty much good to go. This is all we need. Cool. So let's go ahead and extract some sequences. So right now, all I've done is show it on one sequence. Let's go ahead and extract some sequences from our data set. So we'll say seeks is going to be equal to, let's say seeks is this. List seek for seek in so I'm only going to concern myself with a certain subset of these sequences, but I'm going to now pull them all down for our sanity's sake. Missed an S. Perfect. These are all the sequences that I want. Now what I have is a nice big array of the sequences in their original character representation. And when I create my data set object, seeks one initial two are given. Oh, perfect. So now what's useful about this is okay. Oh, I didn't I forgot to return X and Y here. Perfect. So now I get exactly what I put in, right? I put in I can call the first sequence in my list, get back the one hot encoded representation. I can pull out the second sequence, I can pull out the third sequence. I can keep in mind that Python indexes from 0, so everything's off. There's a few comments. Are there any missing values in the sequence data? If yes, are we dealing with them? In this particular data set, there aren't any missing values. In practice, like I would probably just create exceptions or throw away data points that might have missing values and kind of treat them accordingly. It's a little bespoke and depends upon your particular data set and what you want to like, how you want to handle missing data. If you're dealing with numerical data or time series data, maybe you want to forward fill the data or something like this. It's a choice that you have to make. Good. And then Mar, I think you've kind of defined what one hot encoding for us is here, so that's fantastic. Thank you. Cool. So we've created this data set object, and now when we're training machine learning models, often we talk about building batches and things like this. And Torch has a really nice data generator that's going to generate batches on the fly. That's just called so I usually name this torch.utils.data. It's a data loader. Perfect. And it's going to take in the data set object we created and a batch size, which we'll say is 32 for now. This is going to collate. This is really nice. It's useful. It just kind of collates what's coming out of our data set object for us on the fly. If you have sort of custom needs or something like this, you might consider building in some of the custom arguments that belong to this data loader object, right? You might need to do a custom collation function to deal with the fact that things are of different size or something like this. I'm not explicitly considering that here. I'm trying to keep it simple enough. But I go ahead and build this data generator, and now this is a generator object. So if for batch in data generator, print batch, It's going to go ahead. Give me 1 second, folks. I ran into a bug and now I don't know what I've done wrong.
That's okay. So you created the sequences, created that object, data set object. Okay, so now you're trying to print. Okay, now you created the data generator, and then now you're trying to print it. Batch size 30.
Yeah, there's somehow, for some reason, it's returning a none in one limit. Okay, well, I must have messed something up and it's, oh, no, that can't be right, right? For seek when data set. Non-type object can't be interpreted as an integer. Interesting. Oh, I see what happened. I forgot a return statement.
Okay, okay.
Pretty dumb. Coding on the fly, you make these mistakes, right? Now everything's all good and fancy. So now, earlier, what we were only getting was one example of one sequence. We're actually getting the batch size of 32 number of sequences. And the way to see that is that you can see, okay, there's 59 is the length of any given sequence, just so you can see that. Seek's 0 is, these are the characters in seek, len of seek. Perfect. There's 59 characters per sequence. There's 21 possible characters at every position in the sequence. That's 59 by 21 for you right there. Why is this only giving us 25? It's because there were 25 left after iterating through with 32, 32, 32, 32, all the way to the end. So it just kind of says, oh, look, I ran out. I don't have 7 more to populate with. Here's a batch size of 25. If you want to convince yourself that on average or in general, it generates 32, first one is 32, right? So that's generating the first 32. And if we are so crazy to print everything, you can see that it's generating everything of length 32 up until the very last one, because there's only 25 left at that point. Cool. So now we have a batch, which is going to be useful for training, but we don't have a model to train yet, right? We need to build our model to train. Cool. So let's go ahead and build a model to train. So in order to do that, we'll create another class. This is going to be, we'll call it a VAE, right? Makes sense. This is going to be a torch.nn.module. Good. Yeah. Sorry, just checking. Good. And this is going to be, we're going to start by initializing this with a couple of key things. We're going to have an encoder. That's going to be another torch.nn.module, and a decoder. That's going to be another torch.nn.module. And those two things are all we really need for a VAE to work, right? So what is our encoder going to be? Well, we talked about our encoder being a feed-forward network of some kind, right? And that feed-forward networks are often otherwise referred to as like sort of multi-layer perceptrons, which is another torch.nn.module object. And the way this works is we're basically going to have, let's say, self dims. The way this works is we're going to say, okay, we're passing in some input of some certain size, right? And that size in this case is going to be, okay, there's 59 possible positions, 29 possible characters at each position. So the first dimension is how many input features there are. That's 59 times 21. And then from there, we want to, maybe we want to compress it down to 100. And from there, maybe we want to compress it down to 5. Or maybe, and then from there, we want to compress it down to 2. So we're going to build a linear network that's going to compress us from that size to 100, from the initial size down to 100, then from 100 down to 5, then from 5 down to 2. I'm actually going to hard code this. It's not necessarily the right way of doing things, but this is how we're going to do things right here. So the way to do this is simple. So we're going to have a first linear layer, linear 1. That's going to be torch.nn.linear. This is the way of calling a linear feed-forward layer. And it's going to, the first one is going to be the inself.linear.3 equals torch.nn.linear 5 up to 2. You can quickly imagine how this can be made programmatic and customizable and sort of configurable, right? That's not like a terrible challenge. One thing to note here is that for a variational autoencoder, we are embedding into a probabilistic latent space. And in order to make an embedding into a probabilistic latent space, we have to generate, because you can't sort of take a gradient through a probabilistic value, you actually have to do something called a reparameterization. And the way that works is we actually generate the mean value of the embedding. So that's going to be the output of this last layer, and the standard deviation. So sort of the way to do this very straightforwardly is to generate, instead of 2 numbers, 4 numbers. So here I'm imposing that our latent dimension is of, actually we'll do it like this. Here I'm going to impose that our latent space is going to be of size 2. And this first instance is going to be generating means. We call that z mu's, right? And then the next dimension is going to be generating log std. So that's generating the standard deviations of our embeddings. So what you can imagine is now what this network is basically doing is it takes in the tensor that we have. It says, okay, awesome. I have this tensor. Let me project it down and let me predict, okay, the average embedding for this particular sequence should be 3, and the standard deviation on that embedding should be 0.2 or something like this. And that's going to be what we're going to use as our embedding layer. So when you build a custom sort of module like this, you need to define a forward method, which is basically specifying to the model how to operate on like an input. And in this particular case, what we're looking for is, all right, h1 equals self.linear1 applied to x. h2 is self.linear2 applied to h1. And then I've missed specifying that. H2. Good. Awesome. One thing I haven't included here are activation functions, and we should incorporate activation functions into our nonlinearities. These are what give deep learning their power into the forward method. And for our purposes, we'll use a ReLU. Again, this is kind of a choice that I'm just making. People kind of make choices that people make all sorts of choices in this process. So H1. Do that? Yes. Great. Now we have run our activation function on an input. And we're just going to go ahead and return the z-mu and log standard deviation at each step. So this is the encoder class that we're going to be working with. We now need a decoder class. So remember that for a variational autoencoder, the decoder class projects from the latent space dimension size back to the input feature size. And typically these are taken to be sort of symmetric operations all the way through. I'm going to pretty much repeat exactly the same thing that we had described earlier. So this is going to be torch.nn.linear. Now we're going from a space of size 2 to 5, self.linear underscore 2 nn.linear, a space of 5 to 100, self.linear 3 equals torch.nn.linear up to 59 times 21. Cool. That's the network that we're working with. We again have to go back and define our forward method.
Interesting. I mean, like you compressed and then you're expanding to the same dimension, but you
Precisely.
can beyond also, right?
I could, but then it doesn't have a. I mean, yeah, I could, but then I have to change what I'm like. What am I generating, right? In this particular model, the idea is to regenerate what you input.
That's a regenerate exactly what I input. I mean, not exactly, regenerate to the same dimension.
Well, so in practice, the training, what's it called? The loss function objective is to regenerate the input. But if you were to try and say, okay, maybe I don't want to generate exactly the input, I want to generate something slightly different or something like this, I could impose that the model be forced to train something slightly different.
Got it.
Good. Awesome. So we're going to quickly go ahead and iterate through our forward method as we did before. Sorry.
Can I ask a question? Is this going to be classifying as one of the specified amino acids? That's the purpose, is to output a sequence of in the same class that you trained it on?
Yeah. So in principle, the sequences that generate should functionally behave similarly to the inputs. So if I went and took that sequence and generated it in the lab and then did a biological assay on it, it should be indistinguishable from the inputs.
But will the output be a one hot encoded? Will it be in output as a one hot the same way it went in?
Oh yes, good. So the output is going to be a set of probabilities, and that's going to be the probability of each amino acid at each position, and then you can decode that into sequences, into one hot encodings, whatever you like.
But you'll only accept it if it's got a one hot definition.
What do you mean by accept there?
Well, if you had an output that was intermediate between the value of the, let's assume you do a softmax, you couldn't determine. You have to pick one of the tokens that you used in the beginning. It can't be a half A and a half G.
Yeah. So it
has to be discretized to the token set that you started with.
Yeah. So what I'm have the model do here is generate the softmax outputs, right? Generate the probability vectors over each position, and then I, as the I as the person who's now using and trying to draw insights from the model, have to make the decision about how I want to sample from those probability distributions, right? Like there's an abstraction from like, okay, the model is trained to return the probability distribution, and then like the user of the model actually has to make choices about what to do with the probability distribution, right? That's like sort of that's where that is, right? So if you look at like, your favorite example of a chat GPT or something like this, your favorite example of a generative AI model, it is making a choice about like that. It puts out the probability vector and then it makes a choice about what it actually wants to sample from that probability distribution.
So that output end is the same as in a GPT. It's comparing it to a known set of acceptable tokens, and you're choosing one of the tokens based on the probability number.
Yeah, and you should ideally say, okay, whatever the input was, like the predicted output should be the same in this particular case.
Okay.
Yeah. If you were doing like next sentence prediction or something like this, you would say, okay, the predicted probability output has to match whatever the supervised result was for the next sentence, what the next sentence is supposed to be. Right? Masked language modeling is the same thing, except you're just trying to see if you can recover the censored data.
Mm-hmm.
Yeah, all these things are sort of like similar in that way. And RayLu. Let's see if we're gonna find out if I messed up here at some point. And then H5. Good. So now we're gonna get exactly to what you were talking about, which is actually, do I have to do anything here? No, I should stop here. Yeah, good. Great. So now I have something that is of this shape, that is a 59, that is a vector of size 59 times 21. I'm going to go ahead and reshape this. Equals h5 dot view. Hang on. Perfect. So now I think what this should return for us is like, hang on, h5 dot shape 0. Yeah, that's gonna be right. What this should return for us is something where, okay, we have the batch dimension here. So each example is one example from the batch. This is a dimension in the character dimension, and this is a dimension in the amino acid dimensions. And now we're going to softmax over one of these dimensions, right? We're going to get the probabilities over one of these dimensions. And the way we're going to do that is, let's remind ourselves how softmax works. So we apply softmax over the last dimension. Yeah, perfect. Depends on softmax. Dim equals -1, applying it over the last dimension to h5. And then we're going to return h5. So now this is going to be our softmax probability vectors. And we're going to ask the question, okay, when I get these probabilities, do they match up with what they should be? Perfect. Obviously, we haven't tested any of this just yet. We're going to find out whether or not it works fairly shortly. Then we'll just say, now we can set up our VAE. So self.encoder is going to be the encoder that we defined earlier. Self.decoder equals the decoder that we described earlier.
What does VAE stand for?
Variational autoencoder.
And that's the type of model this all is?
Yeah, that's the type of model this all is. Yep. Cool. Have I missed anything here? I think this is all we need to run. So good. Now that we've kind of established this, the next thing we need to do is we actually need to write kind of the forward method for this particular class. So the forward method for this particular class is going to take in, we have this x vector, and remember that x seek is of this shape. And we told our model that we're actually going to give it something that is 59 times 21 in the feature dimension. But what we have is something that is in the batch dimension this, and then has two features, 59 by 21. So we need to first reshape this into something that has the feature dimensions as being 59 times 21. Perfect. And just to make sure that is going to work the way I expect it to, oh, hang on. Perfect. See, so that's going to get it into the right dimensional space. And we can go ahead and get z mu log std out from our encoder. That's what's going to pop out from our input. Great. So here what we have is we've now mapped it into a latent space that is supposed to be Gaussian in some nature, but we've mapped it in such a way that we get the mean and the standard deviation of the mapping. Why do we do this? We do this because one of the constraints we're going to impose is that the mappings generically map the data into a sort of a Gaussian with unit variance. So because you have this sort of Gaussian with unit variance constraint and it's a variational encoder, you're gonna inherently have a probabilistic encoding. You can't take a gradient through an encoding, so we've generated explicitly what the means and standard deviations of our encoded values are going to be. But what we need to do when we actually decode, sorry, the right way of doing this is actually this. Oh no, this is good. This is fine. This is fine. Okay, good. What we actually need to do is we need to sample from a Gaussian distribution with a given z mu and logs, with a given z mu and a given standard deviation. Cool. So how do we sample from a probability distribution in Torch? Torch sample from Gaussian given means and standard deviations. Very sort of straightforward, right? Perfect. We're gonna say return. This is gonna return a tensor that is drawn from it. That is going to return that's basically going to treat every like basically our two tensors of means and standard deviations and spit back out things that are drawn from a distribution with that shape. Perfectly. Z is going to be torch dot normal z mu torch dot exp. Remember, we calculated the log standard deviation here because standard deviations cannot be negative. But it's hard to kind of explicitly enforce that constraint into a neural network model. So the way you do it is you predict the log of a value, and then you exponentiate that value back, because the exponential can kind of always gives us a positive number from minus infinity for inputs from minus infinity to positive infinity. Cool. Torch.exp log std. Yeah, I guess people do log var too. Does this really matter? This might matter down the road in the loss function calculation, but for now it's okay. I'll pay the price for maybe doing this not perfectly correctly in a couple minutes. Now we have a z, right? We have our latent embeddings. That's our z's, and we're going to decode from that. So x hat, which is our prediction for what x is going to come from running the self.decoder on z. And from this forward, we're going to go ahead and do ourselves a favor. We're going to return the average embeddings, the standard deviation of the embeddings, the actual embeddings that we probabilistically sample from, and then our predictions. So in principle, this is now all you need to have like a forward model or something like this. So if we go ahead and actually, run this on, if we say, okay, example VAE, if we go ahead and run this, yeah. I actually didn't need to specify that. That's fine. Did I typo somewhere? Let's see. Cannot assign. Oh,
Don't you have to pass the variable?
so I have to do super.
Okay.
It has to inherit from the class. I forgot.
Okay.
It needs this. Perfect. Cool. So I have an example VAE now. If we go ahead and just take a look at what that looks like, we have our encoder layer, we have our decoder layer. And remember, we have an example X that we can work with. We can kind of go ahead and straightforwardly push that through. So again, remember, this returns Z mu log standard deviation Z X hat. And if we look at the predicted X hats or something like this, it's of the right shape. And if we go ahead and peek at one example of an X hat, this is that probability vector that you were asking about there, Mar. You can see that it's generating a bunch of probabilities for each amino acid at each site. So this is kind of the set of probabilities that for the 0th example at the 0th position. You can look at the first one, you can look at the second one. But this is all like this is sort of okay, operationally this is all great, but now we need to actually ask the question like, hey, I need to actually do something with this. This model needs to be trained, right? I haven't discussed any training whatsoever in this process. And so to discuss training, what we need to do is we need to start defining a loss function in something, a loss function in things of this nature. So we'll first start by, so if we recall from our earlier conversations, variational autoencoders are broken into two components. While the first part of the loss term is based on reconstruction, so we can define a recon loss method. I guess these are technically all static. It doesn't matter. Many of these are probably considered typically static methods or something like this, but because there's going to be no reference to self, but I'm not going to be so careful and care so much about these kinds of things.
So before you move ahead, right? So you basically took the protein sequence, you use some form of encoding to compress the data, put it into a latent space, and then now you're trying to decode and then recreate that same data.
Yeah, that's precisely what's happened here, right? So this in this line of code, that's precisely what's happened.
Correct. So now where is the loss function coming into picture, and how is it important related?
So now this in and of itself is not doing very well, right? It's not actually generating any meaningful numbers. It's just a random network applied to the data. The network needs to be trained, right? It needs to be trained. And in order to train it, we need to train it to optimize a particular loss function.
Okay.
And that's exactly where we're headed next. We're going to go ahead and...
I mean, like from a time perspective, it's how long do you think, like what else is in the content, just to get an idea?
Yeah, I think this will take another 30 to 40 minutes to get all together.
Okay.
Yeah, adding a training thing is just as much work as what he just did.
Yep.
Yeah. So maybe like, should we just do it as a last session?
Yeah, I think we can.
I think we have a logical end at this point of time. We are able to like see how to encode and decode. Now the next thing can be like, okay, training and making it even better. So if that is good, then maybe like we'll wrap it up.
Sure.
I'm just one more question over here. Why are we encoding and decoding? What is the purpose? Is it just because of storage, or is it because of like noise reduction? I mean, I was just reading a little bit over here. So typically, why do we do it?
Yeah, so I think the question you're asking is quite interesting, which is like, what is the mathematical value of feeding these things through many layers? So,
or maybe a practical value. Like, I mean, typically, why would I'm going back to the basic, dumbest question, right? Why do I even encode and decode?
Right. So at least for variational autoencoders, I think it kind of goes back to what you had introed in the beginning, which is that what you'd like to do is learn meaningful variables, meaningful representations of the data, right? Like you'd like to be able to say, okay, if I encode this down to some small dimensional space, I have a few numbers that describe the entire data set or something like this.
Okay.
And so ideally, those few numbers you can then interpret into some human readable term. Like if we were generating like handwritten digits or something like this, like one number would be the thickness of the digit, another number would be the identity of the digit, another number would be the slope of the digit, would be like how slanted the digit is from the center. So that's the value of compressing, is like
Compressing. Okay.
or value of encoding rather.
Why am I decoding it? Right.
So decode, because like, okay, so if we actually have a meaningful representation, then one thing you'd like to be able to do is you'd like to start being able to treat the numbers and those meaningful representations as control knobs, right? You can basically select on the with the knobs which style of number you want, and you can decode from those knobs an example that has the exact specified thickness, slant, and numeric identity.
A very interesting concept. Cool. I think this was good. So maybe like the next session that we have, and I'm okay to like go even beyond. It all depends on Vedant.
Sure.
But next session we'll continue with the process of the training part.
Sure.
And close it from there.
Sounds good.
Awesome. Okay. Good right. Discussion. Good participation. Do you want to share this in a GitHub or something like that?
Yeah, sure. I can push it to
a
GitHub repo and people can take a peek. Yeah.
Perfect. Okay. Awesome. What is just run in my Mac?
So I'm just running this on my MacBook Air. You will need like the various packages that I installed at the beginning of this. I can create a requirements.txt file or something like that. But
that's fine.
Yeah.
Okay. Sounds good. Thank you so much, Vedant. If you can text me the link, I'll put it in the LinkedIn post as well.
Yep, absolutely.
Okay. Take care then.
Catch you later.
Thank you.